So what do we need to know about these subatomic particles? Subatomic means they're smaller than atoms. So all atoms are composed of the same three subatomic particles: protons, neutrons, and electrons. We now know that there are a lot of other particles in there too. There's muons and bosons and all kinds of stuff, and that's physics, which is interesting, but not my thing. The protons and neutrons have nearly identical masses. The only reason you would need to use these actual masses is for like a homework problem or a worksheet problem. You do not memorize those. And the mass of the electron is much smaller. And, looking at these numbers, it's hard to have an idea of the relationship between them. But if the proton was a baseball, then the electron would be like a grain of rice. So much, much smaller and much less heavy, right? Almost 2,000 times smaller. So kilogram or gram is not a great unit for describing the masses of these tiny, tiny particles. So could we use a metric prefix that would come down to like 10 to the minus 27 grams or something? Yeah, we could. But this was before the metric system. And so they made up what's actually a more convenient unit, creatively called the atomic mass unit, which is used to measure the mass of atoms. Right? The definition seems a little strange. One atomic mass unit is 1/12 the mass of a carbon atom that contains 6 protons and 6 neutrons. So this carbon atom has a total of 12 particles, right? And so the mass of those 12 particles plus little teeny tiny bit from the electrons. Divide that by 12, that's an atomic mass unit. So as a result of that definition, the mass of a proton or a neutron is approximately 1 atomic mass unit. The charges can be measured in coulombs, and there they are, but that's not useful for what we're going to be doing. What's useful is the relative charge. A proton and an electron have the same charge that's opposite in sign. The electron's negative, the proton's positive. And so we can just talk about relative charge. Protons +1, electrons -1. The neutron has no charge. It's 0, right? And then in terms of masses, we can use atomic mass units, and we don't really need that much detail. This is approximately 1 atomic mass unit, and this is approximately 1 atomic mass unit, and this is approximately nothing, right? So for a lot of things, we treat the electron as if it doesn't matter, doesn't contain matter, does not weigh anything. Of course it does. So we should know the names, the relative masses in atomic mass units, and the relative charges of those particles. Matter is normally charge neutral because atoms have protons and electrons in the same number. When it does get imbalanced, when something gets a positive charge, and something else must have a negative charge, and that's not stable, and it's likely to become neutral very quickly and often very dramatically. So examples of that are static electric shocks and lightning. So here's a lightning strike. Because of some things that clouds do, you can get a negative charge that builds up on the clouds. And that can result in a positive charge building up on the ground. And the lightning strike is it equalizing? Some lightning strikes come from the top down and others come from the ground up. Static shocks, if you're wearing socks in the winter, well, actually, it's probably not in the winter. Probably more likely to happen on a hot summer day here. And you shuffle around on the carpeting and then you touch like a metallic door jamb and you get a little shock. By shuffling your feet, you're building up static charge. And then when you touch something metal, it gets released. Anybody have any questions? So we use the number of protons in the nucleus to define which element that is. And this is called the atomic number. It's given the symbol Z. I think it should be A, but it's not. It's Z, from the German word Zahl, meaning number. So the atomic number is symbolized with a Z. It's the number of protons in the nucleus. So in a helium nucleus, every single helium nucleus has 2 protons in it. That's what makes it helium. In a carbon nucleus, we have 6 protons, every single one. If it has 7, it's something else. If it has 5, it's something else. All carbon atoms have 6 protons. We often need to know how many protons an element has, and so this information is on the periodic table. So when we look at the individual squares, this one's nice because it's got the names spelled out. That one doesn't. But here's the chemical symbol, and there's a whole number, an integer, above the chemical symbol. That's the atomic number, the number of protons in the nucleus. So for beryllium has 4 protons in its nucleus. You go to nickel, each nickel atom has 28 protons in its nucleus. So this is a list, a table of all the different elements, and it shows how many protons they have.
Does more protons mean that it's like heavier?
Yes. More protons definitely means it's heavier.
Okay.
Yep. If you have more protons, you also have more electrons, which don't really add to the mass very much. But you also tend to have more neutrons in there as well. So we can define each element using its unique atomic number, the number of protons, and a unique chemical symbol. So chemical symbols, those are on your memorization list, they are either 1 or 2 letter abbreviations. And those are listed on the periodic table. The first letter is always capitalized. If there's a second letter, it's never capitalized. Some of them make sense to us. So the symbol for helium is He. Those are the first 2 letters in helium, right? Well, that makes sense. The symbol for carbon is just a C. But then there's some other ones, like there's several other elements that start with a C. So there's chromium and calcium and cesium. So they can't all be C, right? So calcium is Ca, chromium is Cr, cesium Ce? Cs. Yeah, because then there's cerium. Cesium is Ce, and cerium is Ce. So there's a bunch of different ones like that. Then there's other ones that really don't seem to make sense, like Na being the symbol for sodium. The word sodium has no N's or A's in it. Where the heck did they get that? Well, that's from the Latin name for the element natrium. Okay, so we don't use the Latin name anymore, but We've been using the symbols the same since they figured out what elements were, and so we're not going to change the symbols just because we call it by another name. So the symbols that you see up here are used in every language, but the name of the element could be different in a different language. Like the British, which they also speak English, but they call it aluminium instead of aluminum. Why? I have no idea. And they look at us and they think we're weirdos too. So.
We watched the YouTube video on that last night.
Oh yeah?
It was aluminum first, but somehow it just ended up being that way.
Well, actually, aluminium fits the pattern better because there's gallium and indium and titanium. They're all ium at the end. And so, honestly, it should be aluminium, but it's not. So all of the atoms of a given element have the same number of protons. They do not necessarily have the same number of neutrons. And this is where they had to make a modification to Dalton's atomic theory. So atoms that have the same number of protons but a different number of neutrons are called isotopes. And the prefix iso means the same. So they've got the same protons, but different neutrons. So they're the same element, and yet they're not exactly the same. So if we look at neon, all neon atoms have 10 protons. But some have 10 neutrons, some have 11 neutrons, and some have 12 neutrons. All three of those exist. They have slightly different masses, because if you have an extra neutron, you're going to weigh about 1 atomic mass unit more than the one with less. The relative amount of each isotope in a naturally occurring sample is actually roughly constant. So no matter where you get your neon from, the amount of atoms containing 10 neutrons to 12 neutrons is about the same. Those are typically expressed in percentages, and so those are called the natural abundance of an isotope. If we take the number of protons and add the number of neutrons, those are the particles that have most of the mass, right? We said the electron is like almost nothing. That gives us the mass number. That has the symbol A. I am not going to try to mess you up with atomic number being Z and mass number being A. I'm just pointing it out to you because it's so easy to think that A is the atomic number, and it's not. We can represent the different isotopes using nuclear symbols like this, where this capital X is the chemical symbol, whatever its chemical symbol is on the periodic table. Down here, a subscript to the left is the atomic number. That's the number of protons. So that's the number above the element symbol on the periodic table. The mass number is the total of protons and neutrons. Personally, I think it'd be nicer if they just had the chemical symbol and the number of neutrons, but it's not what they did. So examples. We mentioned the 3 isotopes of neon. So all neon atoms have 10 protons. But these have different numbers of neutrons. The number of neutrons is not shown in the symbol, but it's stacked up so that if you subtract, you get the number of neutrons. So 21 minus 10 is 11, and 22 minus 10 is 12. So the bigger number is on top, the smaller number is on bottom, and if you want to know how many neutrons, you subtract. Another way to identify these is by either using the chemical name or the chemical symbol, followed by a dash and the mass number. So those 3 neon atoms that isotopes that we looked at could be called Ne20 or Neon 20 or Neon 22. And this is just kind of summarizing what they have inside of them. So they all have the same number of protons, but they have different numbers of neutrons. So their mass numbers are different, because this is 10 plus 10 is 20. These are the natural abundances of those three isotopes. It's not split evenly. And the only way you can know what it is you'll look it up, because somebody took the time to figure it out. It's just something that is measured. So 90% are neon 20. About 9% neon 22, almost none, less than 1%, are neon 21.
Is that percentage, is it really like from any source, or like is it like the whole world, like if you add all of them?
That's a good question. So is this from any source, or is this, overall in the whole world? It's from a naturally occurring source. So, like there's nitrogen in the air, right? And if you take the nitrogen out of the air and measure its isotopic, the relative abundances, and you go somewhere else and get nitrogen out of a mineral and you measure it, it's going to have the same natural abundance. Yeah. Now, you can make pure or almost pure, say neon 20, by selecting out the other ones. It's not easy, it's not cheap, but you can do it. So that's not naturally occurring anymore. And these numbers are definitely not exact. And, they're not exactly the same, but they're remarkably close. Remarkably close. So we should be able to answer questions like this. What are the atomic number, mass number, and symbol for the carbon isotope with 7 neutrons? Question?
Yeah, is there any significant differences between the neon isotopes?
So is there differences in their properties between the different isotopes? The differences are very small, which makes separating them pretty hard. But where those differences become important is that some of those isotopes may be radioactive and others are not radioactive. Yeah. So a carbon isotope, atomic number, that's the number of what? The number of protons. So you can think of the proton as being like the personality or the personhood of an atom. It's who you are. I think of the electrons as being like what you wear, right? Your clothing. And you can change those. You can make yourself look different, but you're still you deep down inside, right? So atomic number is the number of protons. So, and that's symbolized by Z. How many protons do carbon atoms have? 6. And then we're asked for the mass number, but they tell us that it has 7 neutrons. 13. So the mass number is the 6 protons plus the 7 neutrons. So a total of 13. And then it's asking for the symbol. So the symbol would be C. And on the left, as a subscript, we're going to put the number 6, the atomic number, and we're going to put the mass number up there. This could also be called C13 or carbon 13. These don't have the 6 in it, because if you need to know the number of protons, you can go look it up on the periodic table. How many protons and neutrons are present in an atom of this? K39. So protons would be how many? 19. And neutrons?
20.
Yeah, so we've got 39 minus 19 is 20 neutrons. Any questions? Yeah.
If every atom's like differentiated between like the amount of protons inside the nucleus, then how does that like result in like changes in like the overall taste? Like let's say we have like copper, right? And that has a higher or lower proton than silver, right?
Mhm.
So have like different colors, different tastes. How do those like little protons, the amount of them change, or, like result in those huge changes?
Those are great questions. Yeah, so how, you got the different number of protons, say, between silver and copper, but they have different properties, right? And they have different colors and different densities, etc. That's kind of complicated to answer. Accompanying the different number of protons, you also have a different number of neutrons, but different number of electrons. And so that's really going to affect the size of the atom, and so that's going to be part of it. But also, certain numbers of electrons are more stable than other numbers of electrons. So when we talk about electron structure, we'll learn that. And that's why, for example, chlorine is extremely reactive, and argon reacts with almost nothing. And yet, what's the difference between them? Well, argon has one more proton and one more electron. The electrons are really what cause most of the differences in properties. When you think about it, we've got just these three kinds of particles, right? We've got all these different elements, and what's the only thing different, really? Number of protons and electrons. It's like all made out of building blocks, right? And then they all line up in the periodic table, and we'll learn about why that's so crazy cool, too. Any other questions? So neutral atoms have the same number of electrons as they have protons. But in chemical changes, atoms can gain or lose electrons. They can't gain or lose their protons and neutrons. That's who they are. The electrons are on the outside, floating around. We'll learn what kind of crazy stuff they do. But you can take electrons off of atoms, and you can put electrons onto other atoms. When you do that, it's not an atom anymore. It's not neutral. It's an ion, because it has a charge. So ions are atoms that have gained or lost electrons. They become electrically charged. So sodium, in a chemical reaction, will often lose an electron. So sodium has 11 protons and 11 electrons when it's neutral. If it loses an electron, now it only has 10 electrons, but it still has 11 protons. So overall, it has a positive 1 charge. Fluorine is an example of an element, an atom that can gain an electron. So fluorine has 9 protons and 9 electrons. Here, we're adding an electron to it. So now it has 10 electrons and 9 protons, and you add those up and you get a negative 1 charge. So the charge is written as a superscript to the right of the element symbol. Positively charged ions are called cations. Negatively charged ions are called anions. So cations are positive. Thank you for that.
Remember that because Persepius also said that.
Did he? Yeah. I didn't make these things up. Yeah, cations are positive. Anions, they both end in ion, but anion has an extra N in it. The anions are negative.
I remember what my high school teacher taught me was the T and the cation kind of is another way.
Oh,
Yeah,
that's good. That's good. So the T in cation kind of looks like a plus sign. That's good. This is an example of where we have You have cation, anion, positive, negative. You have two pairs of things, and we have to remember how they go together, right? Sometimes there's a reason that we can figure out. Other times it just is because somebody decided sometime, right? So then what I like to do is I like to make up reasons, right? I like to make something up, and the crazier it is, the better, because then you remember it, right? So cations are positive. The ion charge is written as a superscript. The magnitude, the number comes first, followed by the sign. So if we have oxygen, oxygen has a -2 charge. So we would write that as O2 minus. We would not write O minus 2. I'm not going to mark you wrong if you do that, but just know that that's not what we do. This looks like a math thing where we have the variable O raised to the -2 power, right? This does not get mistaken for a -2 exponent because you wouldn't write the minus afterwards. So we're not going to do it like that. Here, the charge is just 1, and so we don't write the ones. And we'll find a lot of examples where chemists do not, they just leave out the number 1. It's more efficient. There's a negative charge. It doesn't say 2, 3, 4 or anything else, so it must be 1.